right. Let me first of all give a quick review of what we learned. Okay. We have a surface in this space, right? And this is a normal vector, and then you have a surface patch, and this is a picture we always draw, right? Okay. Then we have the map, and this is A sigma U and B sigma V, and NV and C sigma U, D sigma V. So you get a matrix. And this matrix, and actually, this matrix actually related, the coefficients L, M, M, N, and this is going to be, so this is going to be E, F, F, G, and here's A, B, C, D. Okay. So that's the relationship. Okay. Then, those are the coefficients of the so-called Wingardium map. Okay, the Wingardium map. So the determinant. Okay. Okay. So the determinant of the matrix. Okay, that gives you, and this will be independent choice of the surface patch. So that gives you two things. I think it's K1 minus lambda and K2 minus lambda. Okay, and so you get two eigenvalues. This is the principal curvature shows up here. But on the other hand, this is going to be the determinant of A, C, B, D, minus the trace twice of the trace, so A plus D, okay, and lambda and the lambda squared. Okay. So in order to get K1, K2, you can solve this, but we also have A, B, C, D can be used. It can be and A, B, C, D can be replaced by A, B, C, D is going to be E, F, F, G, the inverse matches L, M, M, N, right? That's how do we do the computation, right? Okay, so now there is no just trace. Okay, so no twice again. So we have then you can find the determinant, and you find the trace using this form. Okay. So we do have let's see. So we introduce the so-called Gauss curvature. This will be the Gauss curvature. This is minus 2h lambda and lambda squared. So this Gauss curvature and the mean curvature. Okay. So the Gauss curvature is going to be K1 times K2, and the mean curvature is half of K1 plus K2. Okay. This definition is independent choice of particular surface patch, but you can compute it using this matrix A, B, C, D. Okay, right. So because this matrix, the inverse can be easily find out, E G minus F squared, and here's I think the G and the E and the negative F and negative F. Okay, so you multiply this out, and using the above formula, we get two formulas for the Gaussian curvature, formula for the Gaussian curvature and the mean curvature. Okay, so we have those two formulas we can use to do the computation. Okay. Let me give you the formula again. So those are the formulas. And now it's okay, right? Yeah. All right, let me quickly go over what I'm talking about. So given a surface, and you have a normal vector field on the surface, right? There are two choices here. You fix one normal vector field, then and then in order to do computation, you have to use a surface patch. Okay, then you differentiate the normal vector field with respect to u and v, because the u and normal vector field is going to be can be viewed as a function of u and v, right? So it's a point to u and v, so it could be function of u and v, so you can differentiate, and then nu is perpendicular n, and v is perpendicular to n, so that's why it can be written as a linear combination of sigma u and sigma v. And this matrix F is going to be, this matrix is interesting. So this matrix actually is going to be the matrix representation of the Venn Diagram map. Okay, so the Venn Diagram map is defined by this formula. Okay, so actually this is going to be, right? This is going to be the this matrix A, B, C, D is going to be the matrix of the Venn Diagram map with respect to the spaces sigma u, sigma v. Okay, and we can use that, and the determinant of the linear map and the trace of linear map can be defined using its matrix representation with respect to some basis, but they'll be independent of the choice of a particular basis. Okay, so so we can use this particular matrix. We define the polynomial. That polynomial, okay, is independent of the choice of a surface patch. Okay, so coefficients of this polynomial are the geometric invariants. One is called the Gaussian curvature, other one is called incurvature. Okay, and that can so if the eigenvalues of this quadratic polynomial K1, K2. Then capital K is just K1 times K2. The mean curvature is half of K1 plus K. Okay. But on the other hand, we are using this particular metric, so you can do the computation and using the first and second one, the fundamental form, right, for the given surface patch. Okay, those are the formula. Okay, so we got this. Now, in the last class, we discussed how to construct surface of a constant Gauss curvature. Okay, so today we're going to focus on the constant mean curvature. Okay, the surface of constant mean curvature. Okay, and actually we are going to solve the problem for both. You know, we can use a surface of a constant mean curvature to find the surface of constant Gauss curvature. And conversely, if we are given a surface of constant Gauss curvature, then you can use that to find another one with a constant mean curvature. That's interesting. Yeah, this is I don't know who did it. I cannot find the name for that, but this is pretty genius idea. Okay. So first of all, we consider the surface. Okay, that's called S. On the surface, you have a normal vector field, right? Now I can find another surface, which is completely defined by the normal vector field. Okay, how do I define? If this is a point on the original surface, then here's another point will be on the surface. It's defined by if I use a vector. Okay, if I use a vector, then in the space, this will be here. This is in the normal direction. It's an epsilon. Yeah, I'm going to use lambda n. Typical that lambda n. Right, more precisely, if that's the point of p prime is p as a vector, okay, and plus lambda n point p. Okay. So this is the origin, right? And this is a vector. And the lambda is a fixed constant. So I'm going to check whether this new set is indeed a surface. Right? How can I do that? I let sigma be a surface patch. Right? For S. And I use this surface edge, right? I can construct a surface patch for the new surface, sigma lambda. This is going to be sigma plus lambda n. Now, more precisely, sigma uv okay. So for simplicity, we let always uv to be the normal vector at the point, okay, at this point, right? Yeah, I'm going to change okay. Write it again. Right. All right. First of all, we have to check when this is going to be the sigma lambda is a surface patch. Okay. All we have to do is just compute its the partial derivatives, right? Sigma u plus lambda and u. Okay. Oh, Okay, since NU, so we can use it. It's negative A sigma U and negative B sigma V, right? So I'm going to combine them into 1 lambda A sigma U minus lambda B sigma V. Okay, so sigma V lambda, right? So negative C sigma U, negative D sigma V. So similarly, I can express it right? It's negative C lambda sigma U plus 1 minus lambda D sigma U. Okay. All right, then do the cross product. Then do the cross product. Right, we want to make sure this is going to be non-zero. So when you do the cross product, I think right. So this times that, right? So 1 minus lambda A times 1 minus lambda B, right? Minus, I think, lambda B, lambda C, yes, lambda B and lambda C. And then sigma U, okay? So cross product sigma U with sigma U is going to be 0. Okay, that's why you have, yeah, that's all. All right, so let's multiply this out. It's 1 minus lambda A minus lambda B minus, it's plus lambda square and AD, and then here BC minus BC. Okay, so it's 1 minus lambda A plus B all right, so you see, this will be the curvature, Gaussian curvature, right? So here's lambda H now, okay, plus lambda square K. Okay, so or you can express in another form, it's going to be 1 minus, yeah, I think it's K1 lambda, 1 minus K2 lambda. That's a couple ways to describe it. All right, so in order to make this one a surface, then you have to make sure this is not going to be 0. Right? So sigma lambda is a regular surface patch if 1 minus 2h lambda minus lambda square k is not going to be 0. All right, great. That could be negative, could be positive. Now, what is a normal vector of the surface lambda, right? S lambda, right? So S, see, this is a surface S, and this will be the S lambda, right? And here's a map sigma, then add normal vector epsilon, right? Lambda. So you get a new surface. All right. So my conclusion is that when this is not going to be 0, that's 0. So what is normal curvature of us? Yeah. what is a normal curvature? A normal vector, okay, normal vector of S lambda. Well, it's almost the same because this is going to be sigma lambda, right? Okay. Since sigma, since we have this identity, right? So this is actually the epsilon n. It's the same, okay? Where epsilon is going to be the sign of 1 minus 2h lambda plus k lambda squared. It could be negative, could be positive, but this is not going to be 0. So we have almost the same power vector. But there's a possibility when lambda is too large, 1 minus 2h lambda plus k lambda squared is going to be negative. So the epsilon could be, yeah, this could be plus, could be negative 1, okay? And there is a, yeah, it's possible if when lambda is small, this is always 1, because when lambda is small, 1 is the term dominant the rest of them, right? So 1 minus 2, yeah, this must be equal 1 if lambda is small, right? Otherwise, it could be, it could be negative 1. All right. What do we want to do? We want to compute the curvatures. Okay. We want to compute the curvatures. So we find out this. Yeah, I'm going to go back to this again. Okay, I'm going to rewrite this in some nice way. Yeah, this too, we already did the computation, right? All right, I'm going to express it sigma lambda u, sigma lambda v. Right. It is going to be sigma u and sigma v, and what is that matrix? I think it's 1 minus lambda a, negative lambda b, and here's a lambda c, and 1 lambda minus lambda. Okay. But that is going to be the matrix minus lambda a, b, c, d, right? Why we needed that? Because I want to, right, find this one, okay, and this is, I'm going to call it, in order to compute the curvature for the S lambda surface, right? Okay. I needed to compute this. Okay, maybe this is A tilde sigma u, right? And B tilde sigma v. Okay, So the curve, as I told you, the curvatures of S lambda, the new surface, okay, are completely determined by those coefficients. So I'm going to express it in that way: negative n lambda u, negative lambda v, okay. And that is going to be sigma u lambda, sigma u v lambda. And here's A tilde, B tilde, C tilde, D tilde. Okay. So this matrix, just like I showed you at the very beginning, it contains all the information, the Gaussian curvature and right. So the Gaussian curvature K lambda, right, is going to be the determinant. Okay, and the mean curvature of the surface is the trace of that. Okay, and then we divide by 2. But we can compare with the original. Right? How do I do that? Because I just already computed, right? This n lambda is the epsilon for lambda. So I got epsilon nu, negative epsilon and v. And this side, we have this identity, right? We have this identity. So I can have sigma u, sigma v, and here the matrix. Okay. This is actually the identity matrix, right? 1, 1 minus lambda A, B, C, D. Right? Then you have A tilde, B tilde, C tilde, D tilde. No, sorry, this order is that is C tilde, D tilde. Okay. All right. But on the other hand, this is the epsilon, right? And we know that this is going to be sigma u, sigma v, and here's A, B, C, D. Right? Right. So now we have an identity. Forget the math basis. We have an identity. A, C, B, D equals 1, 0, 1 minus lambda A, B, C, D, and here A tilde, C tilde, B tilde, D tilde. Okay. So what do we have to do? We find the inverse, right? Yeah, that's linear algebra. So A tilde is that is an epsilon of this matrix. Inverse A, B, C, D. All right, so if you have the data from the original surface, then you get the data by this one, the new surface. And remember for the Gaussian curvature, right? Yeah. So the Gaussian curvature lambda is going to be the determinant. Right, and this is when it's determinant, I think epsilon square is going to be 0. So it's epsilon square. So what I have here, is just a determinant. Okay. So according to linear algebra, this is going to determine the A, B, C, D, and that is a determinant of this matrix. Right. All right, so let's multiply this out. This is going to be just curvature. Okay. And here actually is going to be 1 minus lambda A plus D plus lambda square A, D, B, C. Okay, so actually it's 1 minus 2 lambda H plus lambda square K. So you get a formula for the Gaussian curvature, in terms of the original classical and mean curvature. Yeah, how about the trace, right? The mean curvature, right, is going to be half of the trace of this matrix, right? The above matrix, right? So the inverse like A, B, C, D, right? So we have to find out what is that. Let's do the computation. Okay. I'm going to, yeah. So let me write this, right? So this is actually the 1 minus lambda A minus lambda C minus lambda B and 1 minus lambda B, right? Here's A, B, C, D, D. That's the inverse. So we have to find the inverse. Inverse, the first one is going to be the determinant, right? Then the matrix 1 minus D, and the 1 minus A, and here lambda C. I think it's opposite here, lambda B and lambda C. Okay. Then A, C, D, D. All right. Yeah, let's multiply this up. Okay. This is denominator. The denominator is going to be 1 minus twice of lambda. I think it's just H plus K H lambda squared. Okay. So this is we're going to do the trace, right? So that is going to be the trace. Trace means the sum of the elements of the diagonal. Right? So I have to find out what are the elements of the diagonal. I have to multiply this out to 1 minus D A and the plus lambda. Okay, let me check. Possibly I should have I think this place is still it's a C and a B. Okay. Yes. C and B. Okay. Yeah. So the inverse, right? What is it? Well, now, if we have an A, B, C, D, what is the inverse? First of all, the determinant AB minus BC. And then here's a D and then here's A. I think it's minus C minus CD. Yeah, that would be the correct version. Okay. So here's the BC. Okay, I don't need to know the term on the diagonal. So lambda BC plus 1 minus lambda A and B. Okay, so add them together. Okay, so this is going to be the trace. I add them together on the diagonal, right? So I have a 1 minus lambda A plus lambda BC plus lambda BC plus 1 minus lambda A and B. Okay, let's do the computation. All right, so here I have A plus D, no problem. Right? Then I have a minus lambda AD minus BC, right? Then I also have minus lambda AD minus BC. Okay, so I have twice of that. That's why I take a 2 out. And then I get half of A plus D minus lambda AD minus BC. But this is nothing but H, right? Here's nothing but lambda K. Okay, now I have one, I forgot to put the action. There was an action in front of that, right? Yeah, there's an ipsion here. When you take the trace, the ipsion will be taken out. Yeah, this is it. Yeah, this is just plus minus 1. Okay. So we get a nice formula. The mean curvature is going to be 1 minus 2 lambda H plus lambda, right? And the epsilon here, H minus lambda. And again, the Gaussian curvature is 1 minus 2H lambda plus, and that is going to be just K. Wow. So what I want to do, I want to find the motivation, find the surface of constant mean curvature. Okay. So here's a thing. Okay. The theorem says that if K equals 1 over R squared originally is a constant, right? Positive constant curvature. Then H lambda is going to be 1 over 12. It's constant. Wow. So if you begin with a surface with constant curvature, okay, then so I choose R to be lambda to be R. And that's the first statement. Second statement, if the surface has constant curvature, Actually, here's a plus minus sign. Okay. If h is a constant, and which can be written like is a constant. Okay. Then kr is going to be 1 over r squared. It's also constant. All right, so this example shows you if you begin with a surface of constant Gauss curvature, then I can construct a surface of constant mean curvature. Okay, and if you're given a surface of constant mean curvature, I can find that surface of Gauss. Yeah, how do you prove it? Proof is pretty straightforward using Lambda identity. Right. Yeah, let's do it, okay? And which formula again? Okay, we are going to assume prove the first one, right? K equals r squared. So lambda is going to be plus minus r. K is going to be 1 over r squared. So I'm going to plug into I'm going to plug into above formula. Right. So h lambda. The formula says it's going to be epsilon, right? H minus r, right? I is a lambda is a plus minus r, is r squared. And it's 1 plus 1 minus 2 lambda. Right. And here's h, I don't know. Right, then lambda square, so it's r square. K is 1 over 1 over square. Let's simplify. And that will be 2 minus I think we can simplify this. Okay. How can I do that? Okay, you simplify the above one. Okay. I can multiply both sides by plus minus r. So I get epsilon plus minus r h minus 1, 2 plus minus r h. Okay. So that is going to be the difference, right? It's just negative 1. Right, so it depends on the sign here. Okay, so we don't get exactly, I think there's a sign here, right? Negative epsilon plus minus. Plus minus sign and 1 over 2. Anyway, it's constant. Now, when this is going to be, it depends, right? If I choose our epsilon is plus minus 1. So let's go back. If we choose lambda to be oh, anyway, so in either direction, right? I think I could modify this if minus epsilon plus minus 1. So it depends on the sign. Okay. So actually we got more than that. This is going to be depends on the sign, right? So this could be plus minus 1. All right. All right. So now let's look at the second. Okay. If we assume that the mean curvature equals 1 over 2r. Okay. So I'm going to take a look at k r. Okay, when lambda is equal to r. Okay. So we put into the formula. Okay. This is a k, right? Remember k 1 minus 2 lambda h plus lambda k, right? So here is k. So this will be cancelled out. Lambda is r. H is 1 over 2r. And here I is an r squared and k. And you will see that it's just equal to 1 over r squared. Right? So you get a constant curvature. All right. Yeah, that's it. Okay. So you have a surface of a constant. The surface is not necessary to be around the sphere, where it was constant Gauss curvature. Then you extend it, right? So let's have two pictures. One is this is a k equals 1 over r squared. And then this surface here, right? This is surface. This is S. This is SR. Right? The mean curvature is going to be constant. And conversely, if the mean curvature is constant, then we can construct a surface Gauss curvature is constant. All right, so that's a picture, right? And now we're going to look at some examples. Okay, how to construct surface of a constant mean curvature. In the last class, we used a surface resolution and to find the equation so we can get a surface of a constant Gauss curvature. And we use the same idea to construct it, right? But this time I make it easier. I just don't want to have a, I can do like this. Here the x-axis is y-axis. I can construct the y equals f of x, right? And then I rotate around the x-axis. So this surface, that you can have a surface patch, sigma. Okay, the x is the x, and this would be y. You know, this is a point x and y, right? And that would be cosine theta, y cosine theta. All right, so now we have to do the computation. They view y as a function of x. I'm 100% sure I'm going to get an equation in the equation, okay? Right? Then you do the computation. Okay, let's do it. We have time, right? So sigma x is 1, y prime cosine theta, y prime sine theta. Sigma y, right? And that is going to be sigma theta. That's okay. And so E, right? E is going to be what? E is going to be 1 plus this y prime square. So I'm going to use this one, otherwise it's easy to confuse, okay? F is going to be 0, G is going to be y squared. Yeah. Okay, y is a function of x. Okay, now what? Now we have to take the second fundamental form. Okay. So let's compute the normal curvature. Okay. This is ijk. I'm going to get dy dx cosine theta, dy dx sine theta. So this is the first component. The second component here is going to be negative this matrix. So negative y cosine theta. And this will be negative y sine theta. Okay, let's compute this one. So dy over dx and the y. Okay. Negative y cosine theta, negative y sine theta. Then you have the normal vector, right? All right. So this is going to be what is this, right? The length of this is going to be y squared plus this. So y square 1 plus dy d. That's the length. Okay. Divided by, right? Not too bad. After you simplify, the y is gone. So you got dy dx, negative cosine theta, negative sine theta, and here's the square root of the derivative. Okay, this is my normal vector. Great, we keep it. All right, so now I'm going to find the LMN, right? Sigma x. Keep forgetting this. So first component is going to be 0. Right? Just differentiate the y variable with respect to x. Okay. That's x sigma theta. This is negative dy dx, sine theta, dy dx, cosine theta. Okay? And theta said I have to differentiate with respect to theta. Where's this one? Okay, it's going to be cosine and sine back. Okay. That would be yeah. Okay. So LM, right? This is a product with this. Yeah, that is going to be cosine square plus sine square. Actually, it's going to be negative. Okay. Right. Sigma x the dot with the normal vector. And let's go back to by definition of this second fundamental form. Right, this is a sigma xx, the dot product with the m. Right. So this is my n, right? So this dot product, I get a negative. Yes. Right. So m I think it's going to be 0 because they have the opposite sign. Theta. So m is 0. N is going to be negative. Negative becomes positive. Okay. Yeah, well, I'm going to double check my formula here. L is going to be sigma xx dot n. Okay. Our n because I look at the formula in the book, which is different from mine. That's fine. I think my computation is correct. Okay, sigma, the dot product of this two. Okay. Sure. Okay, so that is M and N, right? Then the mean curvature, right? The mean curvature is, it's given by the formula. Oh, oh my God, this is yeah. I cannot memorize the formulas, unfortunately. Okay, so that's yeah, that is given in the book. And let's go back to the page. Yeah, let's slowly reduce the complication. We can see that. Okay. 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 So let's see. H is half of, okay, EG minus F squared, LG minus 2MF plus NE. So MN is going to be 0. That's fine. So EG minus F squared. What is EG? EG minus F squared. So EG minus F. So this time that's Y squared. Okay. So that is going to be Y squared. Okay. 1 plus dy dx squared. Okay. Now L, right? My L is a negative sign here. And have a square root. Now what is my G? Okay, G is going to be LG, right? So G is Y squared. Okay, let's go back to here. G is Y squared. So multiply by Y squared. And plus N. N is the Y of this square root, right? And the E, okay, E is this function. It's going to be square. So from here you can tell. All right, let's simplify. It's divided by 2, so 2 is keep it here. Then I have this part. Yeah, this first part is here, so it's a y, and cancel this term. It's a square root of 1 plus dy dx squared. Okay, and then this part is minus, and y squared is gone. And this will be 1 plus dy over dx squared 3 over 2. Great. Perfect. Okay, so now you see the mean curvature is given by this. You get the equation, you can find it, right? But I'm also curious about the Gaussian curvature. Gaussian curvature is Ln minus m squared, Eg minus f squared, right? So the product L times m, L times n, I think is just negative, right? Negative y d square y dx square, and this is 1 plus dy dx square, right? Because the square root is going to be square right now, right? And this will be Eg minus f squared. So after you simplify it, you're going to get you're also going to get this equation, right? So to construct the surface of constant Gaussian curvature, if only if, right? So this is the surface of revolution, right? Okay. So k equals a constant, positive constant, right? If and only if, right? This equation, d square y dx squared, is going to be multiplied by, yeah, equals 1 over r squared, right? It's going to be negative 1 over r squared. You can just solve this equation. this is fully nonlinear equation, right? But you can solve this. You can describe it, okay? And h is going to be 1/2r is constant for some r, if and only if, right? If and only if you get the above equation. So where's my h? It's a little bit more complicated. Right? It is a little bit more complicated. Okay? So if and only for 1/y, so this is 1 part dy over dx. It's going 3/2, and that is going to be 1/. Well, that equation is more complicated. But there is a way to describe it. I'm not going to talk about here. So you cannot express y as a elementary function. Okay, you cannot describe y using sine, cosine, or this thing. Right? And but according to ODE, for any given information, if you have a initial point and then initial direction, the derivative, you can have a unique curve satisfying this equation. Then you have to solve it. And the surface you're going to get is a constant curvature. Right? It's interesting, right? So you can use a computer, plot, we call the Ode plot. So you're not given formula for the function y equals f of, but you are given the equation. And the computer can find a numerical solution, and then you plot the points on the xy plane, so you can get the 3D. But then you can also you can get a 2D picture curve, and then you can also use that curve. You can and draw the surface in the space, in the 3-dimensional space. Okay. Then you can see what kind of surface could be, right? And then you can also look at the so-called minimum surface, because later on I'm going to mention that mean curvature 0 is called the minimum surface, right? And there are lots of people who study minimum surfaces. It's a long history, okay? And we can construct minimum surfaces right now using computers. It's much easier. So when we start geometry, the first thing we have to do is to what kind of surfaces are curious that can be constant, okay? And we end up with an ordinary differential equation of the second order. Okay. All right, let me stop here, and as long as you have the correct formula, many homework problem, you can do it directly. You just solve the problem and just plug them into the formula.